We're going to pick up in section 1.2 where we left off. And I'm going to begin by talking about a piecewise defined function. Sounds harder than it is. Often we'll just call it a piecewise function. So a piecewise function is kind of just what it sounds like. It's a function with different pieces. So if we have function notation, f of x equals 3x minus 4 when x is less than 0, and 3x plus 1 when x is greater than or equal to 0. Normally, we just say f of x equals 3x minus 4, and we know that we can plug in any value of x. Well, this time, different things are happening to the function based on where we are according to 0. For all the numbers that are less than or equal to 0, so all the negatives, we're going to use this piece of the function. But for all the positives and 0, we're going to use this piece of the function. So that's why it's called a piecewise function, because it has separate pieces. And just like it's got separate pieces here as it's defined, its graph also has separate pieces. So the way I usually graph these is I would look at the top one and I would think, well, how do I graph y equals 3x minus 4? Well, that has a slope of 3 and a y-intercept of negative 4. So we'd start out at negative 4 and put a point, and then I would rise 3 and run 1 from my next point. And I would do that again. I would rise 3, so 1, 2, 3, and run 1. And there's my graph growing, but actually I'm going the wrong direction, right? This is 3x minus 4 when x is less than 0. So instead of rising 3 and running 1, I can go down 3 and left 1 and still be on the same line. So it's only this piece of the graph, and need to be a little more careful here. I do. That's not a closed circle there. Eek. That was an open circle right there. So I don't need this piece of the graph that includes these points up here. So there's that piece. And then we'll just do it for the second piece as well. We've got y equals 3x plus 1, as long as x is greater than or equal to 0. So you can plot it using what you know about points and slopes, or you can make a little table of values. And this is true for all x is greater than or equal to 0. So why don't we say, well, if x is 0, what's y? So you could plug a 0 in here. So it's 3 times 0 plus 1. And you could say if x is 1, what's y? So it'd be 3 times 1 plus 1. And if x is 2, what's y? So you could do that. You could put this into y1, and you could go to your table and get these table values. Or you could put this in y1 and this in y2 and only look at these certain pieces. I think that's more difficult to do, though. But this choice is up to you. So going the other direction, I have the point 0, 1, I have the point 1, 4, and the point 2, 7, and so I have this piece of a line. And this is a function. It does pass the vertical line test, even though I've got a closed circle and I have an open circle down there. So even though x equals 0 has two different values, it looks like one of them is an open circle. So this is a piecewise defined function, and we can use it to answer questions. So let's say for this example, I wanted to know what f of negative 3 was. I asked you, what's f of negative 3? Well, you need to know which piece of this function you're going to plug that into. So you're going to plug it into the piece at negative 3, so x is negative 3. So which one of these x values here works? Well, it's less than, right? This is the negatives. So I'm going to plug it into the top half. So I'll be using the 3x minus 4 piece of the piecewise graph, or the function. So my 4 didn't copy very well. So we're just going to plug in negative 3 in for x. So that's 3 times negative 3 minus 4. Negative 9 minus 4, negative 13 for f of negative 3. And let's say I want f of 0. I want to evaluate the function at f of 0. Then you are, again, going to these two pieces, and you're saying which one of these is good for x equal to 0, and it's the bottom one. The bottom one is defined for x greater than or equal to 0, so that's the portion of the graph that we'll use. We'll use the 3x plus 1. So if x is 0, we'll plug a 0 in, and we'd get 3 times 0 plus 1. It'd be 1. You can also use your graph. You go to x equals 0, and you go up or down till you hit that function, and you hit it right here, and that function's value was 1. So you could do that for negative 3 also, but I didn't carry my graph all the way out to negative 3. So you would have to have gone further with your graph. All right, so those are piecewise functions. There's a good one in your book also on page 19. You might want to look at that. It's example 4. The last thing we'll talk about in this video is the idea of domain. We've already briefly touched on it. Domain of a function can be explicitly or implied, can be, I can't talk tonight, I'm sorry, can be described explicitly, or it can be implied. So for an example, if you have f of x equals x squared plus 7, this is implied to be true for all real numbers. And if you have f of x equals x plus 8, for all x greater than or equal to 2, this is explicitly described because I told you only for x greater than or equal to 2. So it's not super important that you are able to state the difference, but I wanted to tell you the two differences. Okay, we'll be doing example 5. Find the domain of g of x equals 4 over 9 minus x squared. So domain has, we want the domain to be all real numbers. But sometimes it's not. sometimes there are limitations on the domain. So there are two problems for domain: dividing by 0 and square roots of negatives. So this problem, because it's got a fraction or division piece to it, is going to possibly have a problem with our domain, and it's probably this division by 0. So we want to take the denominator and we want to say this denominator is great as long as it's not equal to 0. So we'll solve it for x. So we'll add x squared to both sides. Then we'll take the square root of both sides. So this problem is actually great for all x's that aren't 3 and negative 3. So you might say all real numbers except 3 and negative 3. And we'll work with set notation in a day or so also to help us out on that. I think that's as far as I'm going to go today.